Today I'm going to talk about conformations in organic chemistry. A conformation in organic chemistry is the shape that the organic molecules adapt to as they rotate around their single bond. They can be drawn in two ways: line style, which will look like this, where you can see how the hydrogen is behind with this dotted line, whereas this hydrogen, the triangle, shows that it's actually coming, the hydrogen's coming towards you. Or they can be drawn with Newman projections, which look like this, which would be the same as if you're looking at this carbon straight through this way. So this hydrogen is at the top, whereas this third hydrogen is down here and the second hydrogen is down here, where these three hydrogens are in place on the adjacent carbon. If we look at the rotation of ethane and rotate it 120 degrees clockwise, we can see how this first hydrogen rotates down here and takes position where the H3, the third hydrogen, was. And then this would rotate again to where the H3 is if we rotated it a further 120 degrees. And from that position, if we rotated it a further 120 degrees, it would actually end up back here in this original diagram. This again is showing the rotation of 120 degrees. It's a bit easy to see how this hydrogen here comes down here to where the H3 was, and this is a staggered conformation. However, if we rotate the hydrogens at 60 degrees, you can see how this hydrogen now is here eclipsing the hydrogen behind it. This is called an eclipsed conformation. A staggered conformation, such as this, when the hydrogens on the adjacent carbons are as far away from each other as they can be, whereas for an eclipsed conformation, the hydrogens on the adjacent carbons are as close together as they can be. And for ethane, these are the only two conformers, the staggered and the eclipsed, as you're only dealing with the hydrogens. If we look at the relative energy graph of ethane, you can see how the energy is at the highest here for the eclipsed conformations. This is due to the electrons in the bonds repulsing each other as the bonds are too close together in these eclipsed conformations, whereas down here you can see the energy is a lot lower for the staggered conformations due to the bonds being as far apart from each other as they can be. If we take a look at butane, which is a lot more complicated, as it now has 6 different conformations, 4 different names. We'll start with the anti, where the methyl groups here are completely opposite each other, the hydrogens are completely opposite each other. Then if we rotate it 60 degrees, you can see that the methyl group is eclipsing the hydrogen down here, which I have accidentally covered up by the title of this conformation, is actually eclipsing the methyl, and here the hydrogen is eclipsing the hydrogen behind. Again, this is a opposed conformation, which rotated 60 degrees becomes a gauche conformation, where the methyls are close together. Rotated another 60 degrees, it becomes an eclipsed, where the methyl is eclipsing the methyl, the hydrogen is eclipsing the hydrogen, and this other hydrogen is eclipsing this hydrogen. It then is rotated into another gauche conformation, which then rotates into another opposed conformation. And then if we actually rotated this 60 degrees, it would rotate back into the it would become the anti-conformation again. Now these actually have different names. they can be referred to, the anti can be referred to as anti-periplanar. The opposed can be referred to as anticlinal. The gouge can be referred to as the synclinal, and the eclipsed is a syn-periplanar. Now if we look at the relative energy graph of butane, we can see that the higher energy here are for the syn-periplanar, which then dip down into the synclinal, or the gouge, which rise up into the opposed and then dip down into the anti-periplanar, being the lowest energy value. Thank you for listening. Well, thank you for watching.